Okay, good morning, everybody. I hope you all are doing well. Looks like we're going to have some nice weather for the next few days, so maybe people will get a little chance to get outside and stretch your legs a little bit and enjoy some of the nice weather we're going to have. So today I'm going to talk about graphs of logarithmic functions. This is a little bit tricky. Um, I'm only going to give you one example today. This lecture is going to be fairly short. Please remember as you try the practice problems that if you have any issues with it, feel free to email me, send me a message over Google Classroom, but I will post a follow-up video on the next day. I post a lecture on how to complete all the homework problems, which will hopefully answer questions that you might have on the problems as well. So let's get started. So what I'm going to show you how to do is how to sketch the graph of a log function. In general, log functions all look pretty much the same. There's a little bit of variability based on what the base is of the log, but it's really not that much. But in order to sketch the log function graph, we can actually use the fact that the graphs of inverse functions are reflections of each other about the line y equals x. And so the way this is going to work is I'm going to have you graph this function right here, f of x equals 2 to the x. And once we graph this function is the inverse of this. Notice that the base of the exponent matches the base of the log. When that happens, these are inverses of one another. Now, these aren't super complicated ones. There's nothing else happening other than the base and then the power, which is x. But these two are inverses of one another. And if you remember from when we were discussing inverses, inverses are reflections of each other along the line y equals x. The other thing to keep in mind with inverses is when you have ordered pairs from a function, if you swap the x and y's, you get the ordered pairs of the inverse. And so that's what we're actually going to use in order to graph this. So the first thing I'm going to do is I'm going to just write this as y equals 2 to the x. Now you'll have to bear with me because I'm going to do some writing and erasing on my iPad. But here's what we're going to do. We're going to make an XY chart. Let me back this up real quick. I'm going to get rid of that so it's a little easier to see. We're going to make an XY chart for this function right here. And so when we graph exponentials, it is best to put 5 points, and we're going to use -2, -1, 0, 1, and 2. If we start with the easy ones, I'm going to start with putting 0 in. If you have 2 to the 0, that's equal to 1. If you have 2 to the first, so 2 to the first, so I'm taking these x values right here, and I'm plugging them in right there to that x. Okay, so 2 to the first is 2, and then 2 to the second is 4. All right, so let me get rid of that scratch work. Now, the two that are a little bit tricky, in case you don't remember, is what a negative exponent does. So if I have 2 to the -2, that is 1 over 2 to the second, which turns into 1/4. The second thing is 2 to the -1, and that's 1 over 2. So these turn into that. All right, now why did I show you that? Well, if we were to graph this, these ordered pairs, I'm actually going to go to the next screen and show you what that looks like. Here's the table that we constructed. When you plug in these x's, these are the y's you get, and there's the graph that you get from the exponential equation. Pretty easy. Now, before we graph this log function, I want to show you something. If I take this exponential function, I make it y equals 2 to the x, and then I take this logarithmic function, and I first substitute a y in for g of x just for ease of notation. Remember the very first log rule that we learned. The very first log rule that we learned shows us how to take something from logarithmic form and put it in exponential. So this would become 2 to the y equals x, which is what we have here, 2 to the y equals x. Now I want you to look at this that I'm circling, and I want you to look at this. This says 2 to the y equals x. This says 2 to the x equals y. If you notice, the x's and the y's switch. The reason why they switch is that's what happens when things are inverses of each other, and that's actually how you solve algebraically for an inverse. You switch the x and y's and resolve for y. So this function, this shows us this exponential function and this logarithmic function are inverses of one another. So we already made a table for the exponential function, and it's pretty easy because you know how to take 2 to different powers. Well, then to get the graph of the logarithmic function, all we have to do is take these x's and make them y's, and take these y's and make them x's. They all flip. And that's where this table comes from. So the y's all became x's, the x's all became the y's. And when I graph these ordered pairs, this is the graph that we get right here. And as you can see, this graph of the log is a reflection of the exponential graph. So it is much easier, in my opinion, to take an exponential function, come up with a table, because you know how to take 2 to a power, and then flip-flop the x's and y's to get your graph for your logarithmic function. One thing to notice about this, this graph right here is basically the parent function f of x equals log of x. If the bases change, if it's log base 2 versus base 10, it changes the shape very slightly, but it's not enough to worry about it. So we have 8 parent functions. This would actually be the 9th parent function that we have, which is the log of x. It looks very similar to the square root of x. However, the square root of x starts at 0 and stops right here. This graph actually goes down forever. Couple points about the graph of the logarithmic functions. Um, it, the domain, as I just said, it does go down forever. However, it never actually hits the y-axis, and it never goes to the left of the y-axis. So the domain of this function is from 0 to infinity, noticing that there's a parenthesis on the 0 because it never touches 0. The range, though, it goes down forever, so that's negative infinity, and this does continue to rise forever, so it's positive infinity. So the range is negative infinity to positive infinity. The x-intercept here is 1, 0, and that's easy to understand why it's 1, 0 when you go back and look at our exponential functions, and you can see that our exponential functions always cross at 0, 1. Therefore, when you reverse that 0, 1 ordered pair, you end up with 1, 0. So it's going to cross right there. This is an increasing function, so as you trace it from left to right, the graph is going up. It is also 1 to 1. If you remember what 1 to 1 means, it just means you basically pass a horizontal line through a graph. If it does not intersect the graph in more than one place, then it's 1 to 1. If it intersects the graph in more than one place, it is not 1 to 1. The reason why 1 to 1 matters is a function has to be 1 to 1 in order to have an inverse. There is a vertical asymptote, and the asymptote is the y-axis. We've not talked a lot about asymptotes yet, but basically they're kind of like a barrier wall that the graph doesn't cross. So this graph will never touch the y-axis. It is continuous. Continuity of a graph means you can basically, the easiest way to look at that is, can you draw it without picking up your pencil? Okay, and that concludes your lecture on graphing logarithmic functions. As always, guys, if you have any questions, feel free to email me or send me a message via Google Classroom. Take care.